video solution for homework 3. So the first question is, what happens to Vref if over time R1 decreases? For instance, it could get hotter or colder, and that would change the resistance of R1, or it could age. That could change the resistance of R1. Resistances, they can just change in time. So if R1 is decreasing, but the potential across the sum of these still has to equal V1. So if R1 decreases, the potential drop across R2 has to increase, and Vref will rise. And you can see that in the equation right here. So the next question is, what if R1 is shorted? So if I put a wire of 1 ohm, 0 resistance across R1, then there can be no potential drop across it, and Vref will equal V1. What will happen to the total current if R2 is shorted? Well, if R2 is shorted, Vref goes to 0, and the total current becomes V1 divided by R1, rather than before, V1 divided by the sum of R1 and R2. And if R2 is opened, or if there's an open anywhere in this circuit, then there will be no current can flow, and because open circuits act like infinite resistances. So now for number 2, what happens to the total current if node A is shorted to ground? Well, let's take a look at that. So node A, understand, is everywhere on this side of the voltage and these resistors, and ground is anywhere on the other side. So all it takes is a wire from there to there of 0 ohms. And what will happen is, mathematically, an infinite amount of current will flow. But in a real circuit, what will happen is that there will be a small resistance in the wire and a small resistance in the power supply. And so you'll get some very large current until either the battery loses all its charge, or the wire heats up, melts, and then becomes an open circuit, and the current goes down to 0. And if we remove R2 from the circuit, then we just get V1 divided by R1. It's just completely out, and I can break it anywhere in here to get rid of R2. Okay. Design R1, R2, R3 to have the voltage at node red 1.5 and at green yellow 0.75. Now I encourage you to read the full blown solution here, but essentially what people tend to mistake is that the voltage drop across R2 is not V-red. V-red is the voltage drop across R2 and R3. And so what you'll notice is that R2 and R3 have the same voltage drop of 0.75, and R1 has a voltage drop of 0.5. Alright, which you can see by these equations here. Again, read that at your leisure. The total current is the voltage divided by the sum of these series resistors. And so we want to make these as big as possible to minimize the current. Since the voltage drop across R2 and R3 is the same and larger than R1, these resistances ultimately will be bigger than R1. So what we'll do is set R2 and R3 equal to 1 mega ohm, and then solve for R1. And we get 666K. Didn't ask you to do it, but the closest one on the chart is 665 kilo ohms for 1% resistors. Question 4, essentially, what will the voltmeter read? And even though adding a voltmeter will put these two resistances in series, and the current will slightly increase, the potential drop doesn't. And so the voltmeter will read the 2 volts. And then number 5, we've had a 1 ohm resistor. Now the thing is that 1 ohm resistor plus the parallel combination of R1 and the voltmeter is so small in that comparison that you can set it to 0, and so that what the voltmeter will read is very close to the battery voltage. And if you only have 3 digits of precision on your voltmeter, you will just read the battery voltage. Same thing in number 6, because even though now RS is 10, it's still so much smaller than the parallel combination of R1 and the voltmeter, right? 10 ohms compared to 909 kilo ohms is 90,000 times bigger, and we'll still read about the battery. Now, question 7 is actually the same, almost the same question as 5 and 6, except RS is now R1 and R1 is now R2. And what we're doing is having R1 and R2 equal to each other at 1 ohm, 10 ohm, 100 ohms, kilo ohms. And you can get the total current. And when I plotted it, I calculated it in Excel, and there's the link if you want. And you can see here's the total current according to that equation. But then, notice, here's the total current when I have the battery divided, just taking into account R1 and R2, not R2 in parallel with the voltmeter. And then calculate the error. You'll see that the error is quite insignificant, and even when the R2 and R1 are approaching 1 mega ohm, meaning they're only a tenth of 10 mega ohms, the error is still below 5%. In question 8, all you have to do is take the nominal resistance values and find the max and minimum combinations. And for 5%, the maximum voltage can go up to 2.63 and the minimum can go down to 2.38. If this is whatever it is you're powering will give you the specification of whether that's acceptable or not, or you need to choose higher tolerance resistors. Now, to design this, you can read the data sheet, and even for 5 volts, there's actual values in the data sheet that you can just plug in. They've already done it for you. But you can use this equation. Now, what I tried to do was minimize the power. So I set R2 equal to 1 mega ohm. And I solved this equation for R1. And I got a negative number. Well, a negative resistance value in this case is a non-physical solution. And you can see that if the sum of Vref and I adjust times R2 is greater than V out, then you'll get a negative number. And when I look at the data sheet, it seems R1 and R2 tend to be on the order of hundreds of ohms, not kilo ohms anyway. So I'll just choose R2 equal to 200 ohms, and I calculate R1 equal to be 66.8 ohms. The closest value on the sheet is 66.5. When I ran the simulation, I got 4.97 volts. So I tried some other combinations, and I got 5.07 volts. Given the resistors have a tolerance, either value of R1 is acceptable. Now, to calculate the power, you can calculate the voltage drop across each resistor and multiply it by the current through the resistor. Or you can just realize that if I adjust this 0, really R1 and R2 are in series. You can find the total current in R1 and R2 to be 18.8 milliamps. And then you just multiply that by V out, not V in, V out, because it's just through these resistors, not the total power dissipation of the whole circuit. And you get 94 milliwatts. Now, I looked at that and thought, maybe I could do better. And if I look at that equation for R1, I can see that I need for a physical solution, Vref and I adjust R2 have to be less than Vout. Now if they're equal to Vout, R1 will go to infinity. So the thing is less than. How much less than? I just made it up. I didn't know if this was going to work or not, but I said, hey, if Vref plus I adjust is 10 times less than Vout, I can solve for R2, get 25 kiloohms, meaning that's probably the biggest R2 I can get away with, then solve for R1 at 12.5, I should get a reasonable solution. So when I started running it in Spice, I found that R1 12.1 kiloohms and R2 23.7 kiloohms gave the closest to 5 volts. I noticed I adjust in the simulation was 55 microamps and not 50. And when you dig through the data sheet, you realize that for this particular part, yes, I adjust is not 50, it's 55. So the thing is even when you read the data sheet, you can read it again and again and still learn something each time. Anyway, the power will now be with these new resistor values, and I got 140 microamps, and now for the current, which then gives me a power of 700 microwatts. Now the problem with this estimate is that 140 microamps is now very close to an I adjust of 55 microamps, and so my power estimate will not be as accurate as it was before. Also, if I adjust should vary due to tolerance from part to part, my voltage supply will vary from part to part. Now I read the data sheet and it doesn't seem to mention I adjust varying. It does talk about V reference varying, and you can look it up to see what the percentage is. Okay. Another issue is that, let's scroll back up. These resistors and this capacitor have a charge and discharge constant, and now I've changed these resistor values by several orders of magnitude of what was in the data sheet, and so I might have to change C1 to account for that. Now if you read through the data sheet, it'll tell you how to do that, and being able to do that is actually something we'll go over later in the course. Bottom line, there's more than one correct answer. Just how do you justify it? Now we just have this voltage reference circuit. The total current, V1 divided by the sum of these resistors, I get 4.5 microamps. And then VA is just the voltage drop across R4, so it's I total times R4. VA1 is the current through, is the potential drops of R3 and R4, which happens to be VA0. I get 49.5. And VA2 is 0.5 volts. And so you can see a logarithmic progression with some simple resistors, where if I was to use this as an A to D, not only am I converting it from an analog to a digital signal, but I'm also taking the log of it. Taking the log of something on a digital computer is actually quite numerically intensive.